Good afternoon. I'm Massimiliano Mattioli. I'm an engineer. I'm working in the SHARK-VIS project. On the first row, you can read the core team working on this project. And I want to thank also the Arcetri people and LBTO and BTI people for the help in the data acquisition at the telescope and in the laboratory. Alessandro has already introduced the instrument, so I won't spend any time to say a lot about it. Just I would add that on the entrance of the instrument there is a folding mirror driven by a piezoelectric tip tilt stage, which is responsible for the stabilization of the beam inside the instrument, and the fine positioning and some other stuff. Why we need a beam stabilization system? Because the benefit from the recentering on the PSF is quite clear from this picture, and we acquired this data during Forerunner experiment. Those are on sky data acquired in the 2015, and the benefit of the recentering of the beam, which can be achieved via post-processing or in real time, is quite clear in terms of recovery of the peak. So even if we can do this in post-processing, is mandatory if we want to perform some coronagraphic acquisitions, or even if we would like to precondition the PSF. This is what we deal with it. With the problem, I mean, this is the amplitude spectrum and the cumulative amplitude of the jitter at our focal plane. Thanks to Guido, today we know that we have also a big component at 127 Hertz. But we also know, thanks to Guido, that the jitter at the camera is way lesser than that one we use in our simulation, which is good. If we want to correct the most of the energy of the jitter, we have to go up to 1 kilohertz. Which leads to a loop period of about 1 milliseconds. But this is our problem, because we have a lot of delays on our road to the acquisition, because we have a delay for the exposure time, for the computing, and for the actuation itself. So if we summarize all the lag time, we can understand that 2 milliseconds it's a big value with respect to what we need. So what we can do? We need a model. We need a model to foresee, to have a prediction of the next step, so we can go ahead and gain some time. But which model we can use when we have a process which is almost random? The answer is, our answer, is to use an autoregressive model, which is a representation of a stochastic model, stochastic process, And we can do that because the autocorrelation function shows that the process is self-consistent, is not decorrelated within 10 milliseconds. So if we choose properly an autoregressive model, we can predict the next step using the previous ones. How do we do that? We do that using a a certain amount of samples to train the algorithm, and then we apply those linear combination of the previous states to have the forecast of for the next step. We went a little bit further. We use a multivariate autoregressive model, which can take into account also the cross correlation between the x and y axis. Then we chose a model. We implemented it inside the Simulink with MATLAB, in which we have the core of the model. In the core of the model, we can find the centroid forecast, which is the multivariate autoregressive model, and the piezo model, the piezo description of the model. We retrieve the description of the model from the physics instrument tuning tool. Thanks to that tool, we can retrieve the behavior of the piezoelectric stage, which has an internal loop of 20 kilohertz. So we retrieved, we acquired the step response of the piezo tip tilt, and then we retrieved the frequency response model for our model to import into the system. The output of the system is that one, and we compared a simple control loop with the PID, and the same control loop, but fed by the autoregressive prediction. So the benefit is big, because we can run the same algorithm with a bigger gain, with 6 milliarcosecond residual, which is a reduction factor of about 3 with respect to the input jitter. This is the same results with the XY axis. Then, before going on the test bench, I would like just to add that we had to choose a strategy for our centroid algorithm. So we explored a lot of ways, but here the main problem is that we need an algorithm which is accurate enough, but also light for the computational time. So our choice is in the end a weighted centroid with the center of gravity, and also a thresholding algorithm. Basically, we switch gradually between the two based on the source light, intensity. This is our laboratory test bench scheme. We injected with the tip tilt mirror the same jitter that we have measured. We plotted just to show that they are basically the same. This is the spectrum, and we also use a guide camera, which is an Android-Zyla camera link connected via PCI Express to a standard computer, and a reference camera to acquire the long exposure PSF. This is the pic from the test bench with the two cameras and the whole bench. This is the piezo used to inject the jitter, and this is the physics instrument used to remove. The same installed in our instrument, of course. This is a result obtained with a star magnitude of 10 and a sig of about 1.2 arc seconds. This intensity is scaled based on the Forerunner acquisition data, and in which we had a state ratio of about 30%. And also the flux is obtained as the expected throughput with Sol. As you can see, we try to estimate the goodness of the algorithm, giving this ratio as estimation of the goodness itself. So we had 46% while the jitter is on, but the system is off with no control at all. And the efficiency is 89% with the jitter on, ABS on, and with jitter off, as the comparison, the reference acquisition image is 100%. Then we do the same test with a grid of different values in terms of magnitude and jitter intensity. When I say jitter intensity, I mean that 100% of jitter intensity is the same obtained from 1.2 arc seconds, and the other are scaled. Based on the Guido Gavido, on what Guido Gavido showed us tomorrow morning, we expect to work about 75% or 50% maybe. But we tested also the system with the worst condition. So the peak recovery is about 90 and is quite the same all over the magnitude we explored. The system seems to fail over magnitude 12.7, due also to the performance we expected. Maybe with the better performances from Seoul, maybe we can go also ahead. This is the same, but in terms of RMS. From this plot, you can see that we have basically a reduction factor of about 3 all over the data we explored. Sorry. And this is the last slide. We integrated the system on the instrument, on the final instrument. And we integrated also the functionality of the automatic beam stabilization inside the control software, the main control software. Basically, the ABS control module is responsible for activating and deactivating the automatic beam stabilization. And it also performs some automatic routines like auto acquiring the star inside the field, then reduces the area of integration, area of interest, and automatically run the loop and so on. It recovers if something goes wrong and etc. You can see the running RMS during the acquisition. That's all.